Hello, everyone. I'm Yupeng Zhang from the University of Maryland. Today, I'm going to talk about our work on attacks for searchable encryption. This is a joint work with my advisors, Jonathan Katz and Papamanthou. So here's the agenda of my talk. First, I'll go through some background knowledge on searchable encryption and then present our attacks. After that, I'll show some experimental results of our attacks and conclude my talk. So let's get started. I'm sure nowadays everybody is using email systems, which means we host our emails on the server side, and the server has access to the plain text of our emails. So privacy becomes a major concern. How to guarantee the privacy of our emails? There are email breaches in real life happening recently. So obviously, we can encrypt our emails before sending them to the server. But then the problem becomes, how can the server still search on the encrypted emails for you? To solve this problem, here comes searchable encryption. Searchable encryption is a crypto scheme that allows a client to encrypt his files, and then in the meantime generate some metadata and upload both of them to the server side. And later, the client can issue an encrypted search query for a particular keyword, which we call it in this talk as a search token. And with the help of this token and the metadata, the server is able to return only those files that contain this keyword, but nothing else. And the security of searchable encryption guarantees that for a semi-honest server cannot learn anything about the underlying content of the files or the underlying keyword of the search token. Since its invention, searchable encryption has a lot of applications in practice. For example, there are products of encrypted storage like sky-high networks and CipherCloud. And there are also developments of encrypted email systems. And the major reason of its popularity is because searchable encryption is very efficient. Searchable encryption only uses simple symmetric key encryptions and hashes such that the crypto operations are usually not the bottleneck, and the overhead compared to plain text search is quite small. However, this efficiency comes at the price of leakage. For example, going back to the figure I showed you before, first, although this search query is encrypted, but it's deterministic, which means the server can learn when the same query repeats. This is called search packet leakage. Second, the server is hosting the encrypted files. Although they're encrypted, the server knows exactly whether a particular file is returned as the search result or not. This is called file access pattern. And for those who are familiar with the constructions of searchable encryption, even if the metadata or the search index is hosted on the client side, this file access pattern is still leaked because the client still needs to query the server for the files. In addition, in dynamic searchable encryptions, in a scenario, if the client has ever issued a search token before, and later he wants to insert a new file into the file collection, then the server can automatically tell whether this old keyword is in the new file or not. Or equivalently, the server can search an old token on a newly inserted files. This is called no-forward privacy. So to sum up, we have search packet leakage, access packet leakage. They are leaked by all efficient searchable encryption schemes by definition. And then we have no-forward privacy. All searchable encryption schemes except these three do not have forward privacy. And actually, the third one just comes out after our paper emphasized the importance of forward privacy. So here, we are trying to abstract the leakage profile and utilize them in our attacks, such that our attacks apply to all or most of searchable encryption schemes instead of any particular construction. So searchable encryption proves its security under this well-defined leakage. But what information does this leakage reveal? So probably there's some relationship between this leakage and the content of the files or the query you searched. But the practical meaning of this leakage is not well understood before. So to answer this question, in 2012, Islam et al. Initiated this line of work by proposing a query recovery attacks, namely an attack trying to recover the keyword under a search token. Later, Katz et al. In 2015 proposed another attack with higher success probability. But there's a big assumption in these two attacks. They assume the server knows all the client's files in plain text, and in the meantime, the server is also hosting the encrypted version in searchable encryption. So this could be potentially a big assumption in practice. It's hard to get. Therefore, in our paper, the main contributions are we study another attack model called file injection attacks. And this attack model is first proposed in the CGPR 15 paper, but is not used for query recovery. Under this attack model, we show that there exist attacks that significantly improve the success probability and eliminate or relax the client's file leakage assumption. Finally, our attacks can be extended to conjunctive search, where the clients can ask for files containing 2 or more keywords simultaneously. So with these results, we suggest to reduce or eliminate the leakage in searchable encryption instead of accepting them by default in definitions. Before going into details of our attacks, I want to emphasize the attack target, the queries. So why query privacy is important? In the practical point of view, first, keywords are just parts of the files. They're extracted from the files. And it's shown before that if the server knows enough keywords, the file content can be recovered. Second, keywords can also be used to classify files, so that with this attack, the server can identify those files with sensitive keywords, and this may help to launch other attacks. In the theoretical aspect, query privacy is intended to be guaranteed by searchable encryption. And if there exist query recovery attacks utilizing the leakage, there might be unexpected vulnerability if searchable encryption is used as a building block for a larger system. So with that said, I'm ready to present our attacks. So first, the attack model, file injection attack. So again, imagine a case of an encrypted email system. A client encrypts all of its emails under the searchable encryption scheme and hosts it on the server. But as it's an email system, the client has no way to prevent anyone from sending him emails. So what if the server sends one to the client? As the client is using searchable encryption, he will process this email, encrypt it, and send it back to the server side. So now the server knows exactly this file is the one he just sent to the client and knows the underlying content. So this is quite similar to the chosen plaintext attack for encryption schemes. And then later, when the client issues a search query or a token from the file access pattern leakage, the server can tell whether this injected file is in the search result or not. So this is called file injection attack. So to argue about the practicality of this attack model for email system is quite clear. You cannot prevent anyone from sending you emails. And even if the client has a legitimate list, the server can simply spoof the email address of a legitimate user and launch this attack. Also, in other scenarios where searchable encryption is used to build a public database or public chatting room applications, the server has the freedom to enter these applications as a regular user and to launch these attacks. So there are various scenarios where this attack model is quite reasonable. So under this attack model, there's a quite easy attack. If the server injects a file containing only one keyword in it, and this file happens to be returned as the result of a search token, then this token must be that keyword. So that's a naive version of the attack. But in this naive version, the server needs to inject a lot of emails containing one keyword each, which is quite easy to detect, to be detected. So Therefore, we present a smarter way in our paper called binary search attack. So let's say we have a well-defined universe of keywords which can be drawn from the dictionary or defined arbitrarily by the server. And then the server injects this file containing half of the keywords in the universe. And for example, the second half as shown and shaded on the slide. And then the server learns that this file is not in the search result of a token. Then he knows that the keyword you search is in the first half of the universe, but not the second half, right? Similarly, if the server injects these two files and the search result is 0, 1, 0, which means only file 2 is in the search result, but not file 1 and 3, then the server can uniquely identify the keyword the client searches is K2, because only K2 can give you this access pattern. And if you think about it, it's actually the classical binary search, and 0, 1, 0 is actually the binary representation of the index of the keyword in the universe. So with this attack, the server only needs to inject logarithmically many files in terms of the universe size, or concretely only 14 files for a universe of 10,000 keywords. After that, the server can recover all queries ever issued by the client with perfect accuracy. Furthermore, this attack is we call non-adaptive. These files can be generated and injected before seeing any queries, and they apply for all the keywords. And in this attack, we only use file access pattern. And as I mentioned before, this universe can be defined by the server arbitrarily. So if the server is only interested in a small subset of sensitive keywords, he can further reduce the number of injected files. So far, this attack is very powerful. The server can recover everything with a small number of injected files. We're done. But not quite actually, because there's a limitation of this attack. So the observation is that those injected files are quite long. Each of the files needs to include half of the keywords in the universe, which leads to a natural countermeasure called threshold countermeasure on the file length. The idea is, what if the client filters all files that contain more than T keywords? Then the server can no longer inject those long files. By filtering, we don't mean delete those files. It simply means that the client can simply index a subset of T keywords from a file that has more than T keywords. So to test if this countermeasure is reasonable, we choose the Eron dataset, which is a dataset consisting of real-world emails obtained from a data breach and is used widely for research purposes. Under a universe of 5,000 keywords, only 3% of the files have more than 200 keywords, which means if the client sets the threshold as 200, only 3% of regular files will be affected. So this is a kind of good countermeasure. And under this countermeasure, the server cannot inject those long files. What can he do now? Then an alternative is, what if the server defines a new universe that is smaller, or namely 2T, of size 2T keywords, and launch the binary search attack? But if the server defines this new universe randomly and inject files based on this new universe, then for a particular token, it's very unlikely this token is included in the new universe, and the attack will fail. So therefore, we propose a smarter way to define this new universe relying on some extra information called partial file leakage, which is actually exactly the same kind of assumption from two prior papers. The server learns a portion of client's files in plain text. And in practice, these files could be obtained through announcement or alert emails broadcasted to a group of people. So with this information, the idea is that first, if you define a term frequency of a token or a keyword as the total number of files containing it divided by the total number of files in the file collection. Then for every keyword in the universe from the leaked files, the server can calculate an estimated frequency, denoted by F star. This is called estimated because the leaked files are a subset of the file collection. On the other hand, when seeing a token, the server knows exactly how many files are returned in the search result. So he knows the exact frequency of this token. Then based on the constraint that the estimated frequency should be somehow close to the exact frequency, the server can, based on this information, to select a subset of 2D keywords as candidate universe, and then launch the binary search attack on top of this candidate universe. In this way, all the injected files will be shorter than T keywords each. And later experiments will show that this attack works with very good probability. Okay, to highlight some difference between this attack and the prior binary search attack, first, this attack is adaptive. Those injected files are generated targeting a particular token, but will not work for other tokens. Second, in order to get the exact frequency, this token must be searched before, and then the server injects those files, and then get the search result on those injected files again, which means the attack applies to searchable encryption schemes with no forward privacy, because here the server can simply search this old token on the newly injected files himself. Or this token must be searched twice, before and after the injection. However, as I mentioned before, almost all searchable encryption schemes has no forward privacy. So our attacks will apply to most of them. Finally, the server does not always succeed. If the estimated frequency is really far away from the exact frequency such that the keyword is not included in the candidate universe, the attack fails. But a very important property of our attack is that the server can determine whether attack fails. Because if none of the injected files are returned, the attack simply does not work, and the server can relaunch the attack with a different candidate universe. This is not the case in the two prior papers. The attacks in the two prior papers succeed with some probability, but the server cannot tell whether it succeeds or not. And we also have a more complicated algorithm targeting multiple tokens simultaneously, and you can refer to our papers for details. So after presenting the attack algorithms, I'm ready to show some experiments. So for methodology, we took the ERON dataset with 30,000 emails in it, and choose top 5,000 keywords with highest frequency as the universe, just to compare with the prior two papers. The settings are consistent. Recall that for our basic binary search attack, we don't need to do any experiments. As long as those files are injected, the attack works perfectly. So here we show some experimental results for this advanced attacks under the threshold countermeasure, but with some extra information from leaked files. So here we are using this figure. The x-axis is the percentage of leaked files obtained by the server in plain text, and the y-axis is the accuracy of the attack. This red line is the performance of the attack in CGPR 15 paper. As you can see, if the server knows all the client's files in plain text, the attack works pretty well. But the performance drops dramatically as the server learns less. On the contrary, the blue line shows the performance of our attack. Even if the server learns only 1% of the client's files in plain text, it still has a successful probability of 30%. And the accuracy approaches 1 quickly as the server learns more. And also the server can know whether the attack succeeds or not, and run the attack again to further increase the success probability. And this performance is under a threshold of 200 keywords for each file, and the number of injected files is always 9 files. It's very reasonable in practice. Here, I want to clarify that this is not a fully fair comparison because we are in different attack models. But here, I just want to show the effectiveness of our attack in this figure. Similarly, here's the performance of attacks targeting multiple tokens. And as you can see, the accuracy is improved significantly, and the number of injected files is always less or equal to 40, which is quite reasonable. To provide some insights why our attacks works better, the two prior attacks relies on the leaked files to build a frequency distribution of all the keywords and try to find the best match between the keywords and the tokens on the frequency information. However, this best match will soon be distorted when less files are leaked. On the other hand, our attacks use this information to rule out those bad matches, to rule out those keywords that are unlikely to be the real keywords for the token, and then search on the remaining ones. So this improves the accuracy significantly. Also, our attacks can be extended to conjunctive search, and you can refer to our paper for details. Finally, I want to discuss some potential countermeasures. As in our attack, for under the threshold countermeasure, we are using the frequency information of the token. A natural countermeasure, which is also proposed in both of the two papers before, is called search result padding. The idea is we want to pad the search result with some random files, some wrong files not containing the keyword, such that multiple tokens will have the same exact frequency. So in this way, the exact frequency information will have a lot of noise in it. And this will ruin the attack algorithm in the two prior papers. However, we argue that this does not work at all against our attack. Because first, we argue this does not affect the basic binary search attack because simply we don't rely on this information. Second, it does not affect the advanced attacks even if we use this information, because no matter you pad or not, closed frequencies are still closed, and we still can use this information to rule out those bad matches. To justify our argument, we show some experiments. First, I want to define a parameter on padding called beta of a keyword k as the number of padded files for a particular keyword divided by the number of files in the original search result. And then beta as the average of all beta k's. So intuitively, if the beta is larger, you will pad more and more wrong files to the search result. So this introduces a higher overhead on the communication, but on the other hand, it should be more secure. But then this figure shows that as we increase beta, the performance of our attack is not affected that much. We still can approach 90% of accuracy as the server learns more and more files. And here's the performance under different beta of the attacks targeting multiple tokens. On the contrary, this slide shows the effect of the countermeasure on the attacks in CGPR 15 paper. As you can see, as beta approaches 0.6, the prior attack cannot recover anything at all, but our attack is not affected much. So this shows that this countermeasure does not work against our attack. To also list some other potential countermeasures, recall that our attacks relies heavily on the attack model called file injection attacks, where the server can identify which file is injected by him. So in a static searchable encryption, the idea is, what if we pad all the files to the same length after encryption, so that the server cannot use this uniqueness of the length to identify the files he injects. We call this partially works because, first, there's a large storage overhead if you do this. For example, in neural dataset, if you pad everything to maximum, it introduces 1,000 times overhead on storage. Second, it only works for static searchable encryption because in dynamic case, the server can simply rely on the timing information to identify these injected files, because the next file you upload to the server is the one he just sent to you. Therefore, we further propose a countermeasure called batched updates. The clients should wait for several files, pad them to the same length, and shuffle them before uploading them to the server. So in this way, the server cannot identify which one of them is the one he injects. However, this again partially works, because even if the server repeats the original attack with one injected file per batch, this still succeeds with a very tiny probability. But this probability can be amplified exponentially by repeating one injected files many times. So by injecting a little bit more files, the attack still succeeds with very good probability. So finally, to conclude my talk, we show that the file injection attacks are devastating for query privacy in searchable encryption. And we start to question, is that a satisfactory trade-off between efficiency and the leakage for existing searchable encryption schemes? We may start to reconsider the definition of leakage profile instead of accepting them by default. Some potential future research direction is trying to reduce or eliminate the file access path leakage, or to explore some new settings like multi-server schemes or interactive schemes. Finally, forward privacy is a very important feature for searchable encryption. We are the first to show attacks that utilize this lack of forward privacy to improve the power of the attacks. And we recommend future searchable encryption constructions to always include forward privacy as an important feature. That's all for my talk. Thank you for listening.